Welcome everyone to another session of the data learning seminars. Today we had Drgoňa from the PNNL, and he'll be talking about his library for PyTorch and Neuromancer. Jan, thank you for sharing your time with us, and I'll leave the audience with you.
Yeah, thank you very much, Cesar, for the invitation. It's a great pleasure to present joint work from our team at this seminar. So let me share my screen and you let me know whether you can see it correctly. Let me share it again. Screen 2.
Yep.
Okay, I think, yeah, you should be able to see the slide. So I will be talking about the Neuromancer, which is differential programming library for modeling, control, and optimization that we are developing in our team at PNNL, with core developers being Aaron Tour, James Cook, Madeline Shapiro, Drgoňa Vrabie, and myself. But I want to first give you a little bit of story how we started. Since we are Department of Energy National Lab, our primary interest is to satisfy the requirements of our sponsors that come from various application areas, from basic energy sciences to power systems and energy systems in buildings, where simulations are crucial for all sorts of scientific discovery and decision making. But very often we have these high fidelity simulation models that are too complicated to run in decision making closed loop fashion. So they are very good for inference, for forward simulation, but very expensive for backwards or inverse modeling that is necessary for optimal design and optimal control. So there are numerous challenges when it comes to going data-driven. Yeah, when we want to do surrogates of these complex simulators, we need to come with some verification methods that indeed the physics will be not violated or certain operational conditions won't be violated for safety reasons. And we need to do this in a fast and reliable way. So luckily, the computer science community came up with scientific machine learning, which is a wonderful trend of connecting physics or domain sciences in AI models. So we have seen many headlines how neural networks beat superhuman performance in all kinds of applications. For me, the most exciting things is that what AI can bring for scientific applications like modeling partial differential equations or optimal control. When we look at the landscape of numerical solution methods, there are historically two communities. One is model-based community, or like traditional engineering, where we know exactly the formulation of our optimization problem. So we have this objective function, nonlinear constraints, or we have some differential equation, and we use numerical solvers to obtain the solution for those. There is no learning involved, there is just numerical methods. On the other hand, we have machine learning community where we have all sorts of learning paradigms and all sorts of function approximators where we assume no or very little prior knowledge, and we train these functions from data. So historically, two separated communities that also driven the development of two separate sets of tools. So for people who are coming from engineering domain, and particularly operational research or optimal control, you will be familiar with constraint optimization frameworks like PyOmo or JUMP or Casadi that is control-oriented, and a lot of numerical solvers like Gurobi, Sigplex, or Interior Point, or Nitro that are designed for solving these type of problems on instance basis. But historically, there is no machine learning. Yeah, there is just pure engineering models, solvers, solutions, and the same with differential equation solvers targeting different domains or generic purpose Machine learning tools, they revolutionize deep learning, essentially. That's what we can tell. Like, deep learning is so popular these days because it's so easy to use. Every single one of us can train and deploy deep learning model within a day on a given data set. And we can thank like developers of PyTorch, TensorFlow, and recently like new libraries in Julia like Flux or JAX, making it so user-friendly that all engineering and scientific applications now are using deep learning in some form. But what comes next is differential programming. That's what we see is the trend in computer science and scientific machine learning community, is the junction of these two separate domains originally, where we see more and more numerical computational methods are being used in machine learning models, and more learning is being embedded in traditional constraint optimization and differential equation solvers. So we see differential programming as really the unifying approach, where you leverage the power of automatic differentiation, which we can say when backpropagation revolutionized the deep learning, now automatic differentiation, which is just generalization of the backprop method, will revolutionize scientific computing, because you can compute sensitivities not only of deep learning layers, but of complex computer programs that have differential equations in the forward pass that include conditional statements, for loops, all kinds of things. And as a highlight, only a couple of influential papers that influenced my own research. This is very incomplete and biased list of papers, but something that I found very inspiring and interesting are differential programming, systems to bridge machine learning and scientific computing, has been brought forward by Julia community. Everyone knows physics-informed neural networks for solving PDEs, or neural differential equations for learning surrogates for ODE systems, and more recently, generative modeling, where under the hood, you have stochastic neural differential equations. We have differentiable optimization that act as a layer for embedding hard constraints in deep learning context. And how they work? By propagating the gradients through constraint optimization solvers. So very powerful technologies for generative modeling, for embedding physical constraints, either as a soft constraints or hard constraints. And now when you have all of these capabilities for modeling spatial temporal systems and embedding constraints, it is just one step towards control, where you can learn a control policy that satisfies certain requirements. But when we started to work in this area in 2019, it was 4 years ago, we quickly realized that there are no easy to use open source tool that we can just grab and use and deploy for the applications that our sponsor requires. So we started to develop our own library. We call it Neuromancer. It's written in PyTorch. And the whole philosophy is to basically bring the symbolic reasoning from classical engineering domains like control and operational research on the top of deep learning capabilities, or more recently like these differential programming capabilities. And as engineers, we typically think in these symbolic abstractions. Here is example of small nonlinear optimization problems where I want to minimize this nonlinear objective. I have primal decisions to be X, that's what I want to decide on. And I have some parameters P that keep changing. And I want to satisfy some nonlinear constraints. Traditionally, in numerical solutions, we would need to fix the value of the problem parameter to specific numerical value and call the solver to obtain the solution for X. And every time the problem parameter would change, we would need to recompute it again and again. So here, the idea is to replace this numerical solver with learning-based solver, this mapping pi of theta that will map parameters to primal decision variables, can be neural network, can be function approximator. And we will learn these with stochastic gradient descent. So that's what our library aims to provide, that you go from this high-level mathematical form in the user-friendly API, that you have this intuitive command line interface like you have in tools like CBXPy or Jump. And what this library does is that generates the differentiable computational graph that represents the optimization problem for you. So instead of like having layers of deep neural networks, now you have layers of mathematical operations that represent the optimization problem. So in terms of capabilities, first area that this library allows you to do is to solve or learning to solve constraint optimization problems. And there are two general paradigms how to do that. You can do imitation learning, where you have some ground truth obtained by numerical solvers, and you train neural network in supervision. That's standard approach. However, obtaining this ground truth by solving a bunch of optimization problems can be very expensive. Plus, there is no notion of the problem itself. Therefore, an alternative approach is self-supervised, or so-called constrained deep learning, or end-to-end deep learning, where instead of having ground truth labels from the solvers, you are going to differentiate your optimization problem itself. So you will have the knowledge of your objective functions, equality, inequality constraints, for which you can compute gradients. So very similar idea that was behind physics-informed neural networks. And just for illustration, like here on the left-hand side, we have this GIF that where each frame represents new problem that is changing the parameters, like shaping the loss function or expanding the feasibility domain of this half donut shape. The structure remains the same. You have still the same number of constraints, and functionally they have the same form, but they change the numerical values. So you can train neural networks to mimic the solution from the solver. The advantage is upon deployment, you don't need to call expensive iterative solvers. You will have function approximator. They will give you quick solution. And in many areas, you can obtain orders of magnitude speed up. And that can be a game changer for real-time decision-making. However, because of the nature of differential programming, you are training this with stochastic gradient descent type methods, and very often using penalty functions to obtain the information about the gradients of your constraints. There may be some small violations, sometimes big violations, and we want to have means of correcting those and guarantee the feasibility of these solutions. So there have been a lot of research in so-called feasibility restoration or implicit layers by using those differentiable optimization solvers, like I mentioned before. So that's learning to optimize capabilities. Next set of capabilities is modeling of dynamical systems. So when it comes to ordinary differential equations or network dynamical systems or PDEs, there are a lot of methods out there that demonstrate the utility of some kind of deep learning surrogates to model these methods. So that's what we provide in the library. You can formulate your physics-informed neural networks in a very user-friendly way. We provide APIs for neural differential equations or white box differential equations. And also this component-based modeling, who is from the controls domain would be more familiar with. Like as a control engineers, we are used to build block diagrams, and each block has some mathematical operation and create feedback loops. So these all capabilities we support. And once we have modeling capability for dynamic system, is one step towards doing closed loop control, where given the system model, we can expand the system model with control policy and represent this as a closed loop dynamic system, where the control policy generates control actions that perturb the system. The system generates the response on the rollout, and we obtain the trajectories of the system behavior. And now we can evaluate the trajectories with respect to desired behavior, like track the reference or stabilize the system or don't violate the constraints, avoid the obstacle. And because all of these components are now differentiable, we can do reverse mode automatic differentiation or backpropagation of these values backwards through system dynamics model to train the control policy. And as a training data set, we will use distribution of desired operational conditions like initial conditions or desired references and constraints. So these are high-level capability overview for our library. And next, I want to show some real-time examples before I conclude here. So let me pull the library over here. So as I mentioned, we are open source library. You can find us on GitHub. And we have already a set of Google Colab examples for like first introduction of the Neuromancer library, where we show you the API for the syntax, a couple of examples for learning to optimize constraint optimization problems, examples for dealing with ordinary differential equations, either in a black box way or more like a gray box and white box way, physics informed neural networks for PDEs, and differentiable control. So I'm going to start with some syntax, and then we go at least one example from each category if time allows. So by the way, if there are any questions, please drop them in the chat. I may not see them immediately. There is a question from Ahmed. Is the system model here known or partially a priori? Both. You can either have white box model where you just write down your differential equations, or you learn it from data. And I'm going to show you one example like of this system identification approach. So the first example I'm going to show is the main abstraction which we are using in Neuromancer, and that's the variable class. That's what you are used to when you are building constraint optimization problems. And there are different ways how to instantiate variable in Neuromancer. They are really serving the purpose of pointers to some symbolic expressions. So when we instantiate variable and we give it a string, that string will represent its name or its key that will be expected to be provided in the data set. And our data sets will come in the dictionaries with strings as keys for variable names and tensors as numerical values. So that's what we can see over here. Evaluate this variable, forward pass, and that's it. Nothing fancy, but we may want to have variable that is not pointing to the data set. We want to have some trainable variable that has trainable parameters. So you just instantiate variable without any key, and it will come with some trainable tensor that will require a gradient. You can also define the shape of the trainable variable, and you can have matrices or tensors. And you can also play with display names for some visualization later on, I will show. All kinds of things can be done over here with instantiating variable, also with like predefined tensors, and you can turn on the gradients or not. But what is the most interesting or probably useful is that you can use the command line interface where we overloaded all common operators to construct these computational graphs. So the variable is PyTorch NN module. So it's like quote unquote neural network architecture that is having forward and backward pass. And if you want to have algebraic expressions, like I'm showing here, well, what I'm doing that this x1 is a Neuromancer variable and adding some scalar that will be my new variable that I can use as a layer in the neural network. And you can go really wild in these expressions. Here I have some polynomial, and you can visualize this computational graph. So what is the purpose of this variable is to provide really like easy handle, the symbolic wrapper on any kind of mathematical expression you would like to use. So basically we support anything that PyTorch supports. So all PyTorch callables work not only with tensors, but also with Neuromancer symbolic variable. So here I'm adding two symbolics, A and B. And be aware, right now I'm not working with numerical values yet. I don't assign any tensors. So what it provides you is provided with the flexibility to evaluate the computational graph and again with different values or even like different shapes of the tensors. You can even use a variable to wrap a neural network architecture and provide the symbolic wrapper for this single layer linear model. You can use any lambda callables or any callables in Python and wrap it in the symbolics and create a variable around it. And here I have this quadratic expression, and when I want to evaluate, I have two input variables, x and y, that will represent the symbolics of these. So I'm evaluating variable x, that is x squared plus y. So when I change the numerical value over here, you see I'm changing the values on the x1 variable. Yeah, so that's the intuition behind the use of the variables. Why we want to have these symbolics? Because very often we want to define some physical constraints and some objective terms in this symbolic realm. So for that, it's as easy as, again, overloading comparator operators. Well, I have variable that needs to be less than 1 here. Yeah, so that would be my constraint. And the forward pass of the constraint will give you 3 values. That would be the penalty value, the value of the left-hand side of the variable, and the residual. And you can go and compute or construct more complicated constraints. Here I'm comparing 2 variables. I want to say that x will be less or equal than y, and I can add some weighting term, because when we have multiple terms in physics-informed neural nets, like very often we want to balance them because they may be out of scale. We may want to use like different norms. By default, if you don't do anything in here, you will use 1 norm. When you do this square have 2, you will do 2 norm. And that's how you can evaluate these constraints with some tensor values on these 2 variables. So every time I evaluate, there will be some different value because it's a random generator. Okay, you can also have trainable torch parameter to represent a weighting factor in the constraint. So you can do tuning of your optimization problem in a learning-based way. That works. Yeah, you can have also this algebraic expression, like inline over here, comparing with some right-hand side. And when you want to minimize or maximize certain variable, without knowing what is the target value, we provide this method that is called .minimize. So each variable can be easily used and to directly generate objective function term. So for instance, I have here 2 variables and this nonlinear expression, like I've shown in the previous slide, and I call .minimize, and that's my objective term. Good. Yeah. Another way would be to use the objective class, where you just hand over the symbolic computational graph, this variable, and define some arguments, like what would be the weighting term or what metric do you want to use, all kind of things. So this is our primary layer of abstraction for constructing symbolic computational graphs. Another layer of abstraction would be the node class. This is installed. Need for this. Node and system class. These are very lightweight NN modules in PyTorch that, again, allow you to construct symbolics on the top of neural network architectures. So for instance, I have here the linear layer, and this is mapping tensors to tensors, but I want to make it symbolic. So I'm using this node class that will wrap PyTorch neural network model or NN module and provide the symbolic input and symbolic output. And this can be like arbitrary neural network architecture. It can be arbitrary callable with multiple positional arguments. So I have these two inputs and either return one output. It can return multiple outputs. So two symbolic inputs, two symbolic outputs. And now you have like very user-friendly way of wrapping your neural network architectures in arbitrary form and shape into the symbolic expression. So here we have some predefined multi-layer perceptron, and I wrap it in the node. Here you have some neural network, recurrent neural network, wrap it in the node, make it symbolic. And once I have like these different instances of the symbolic wrappers for various neural network architectures, I can create these component-based models for closed loop or open loop system modeling. So that's what the system class will be doing, which will support this cyclic computational graph that are built on these input-output keys. So here I'm going to, oops, node 2 is not defined. To this cell. Okay, now I have defined list of nodes. Each of them has some inputs and outputs, symbolic inputs and outputs, and I'll hand it over to the system and tell the system that I want to do the rollout, the recurrence of this list of nodes for 3 steps. So you can think of it as really like symbolic recurrent neural networks if you are coming from deep learning community. And now I can show the computational graph of this system. So I expect that in my data set, I will have symbolic x1 and x2 variables, and they will feed node 1 and node 2 that will generate y1 or y2, and I will have this quadratic expression that will generate y3, and this will be my output. And the system will be evaluated 3 times forward pass. So this is acyclic computational graph, but here I can show you that I can generate cyclic computational graphs by just creating loops, self loops. And this capability will be very, very useful when I'm going to show you some optimal control example. So this is the basics of Neuromancer syntax. Are there any questions at this point?
Yes,
yes, great. In regards to differentiable control, is the example essentially learning the value function and using a reverse mode automatic differentiation to extract the cost states from the model, or a generalization of that to a broader range of control problems? Let me show you the example where the idea is not to learn value function, but to exploit the prior knowledge of your system dynamics and prior knowledge of the objective function terms and constraints to construct model-based value functions. So you, instead of doing value function approximation like you do in reinforcement learning, here you will have model-based value functions. So you basically mitigate the risk, the disadvantage of function approximation error in that case. And you are going to backpropagate these signals from the forward path of your causal dynamic systems through this model-based value function to obtain model-based policy gradients. But before we do that, let me show you first learning to optimize. I have it open over here. Learning to optimize is a method that is also called deep declarative networks or end-to-end differentiable control, where you want to solve some parametric constraint optimization problem. So this is exactly the same problem I showed before in the slides. Nonlinear objective and non-convex constraint. So I start with importing Torch and Neuromancer. And everything here starts with sampling the data. So this is a sampling-based approach where we want to evaluate the constraints and objectives on specific values of the problem parameters. Here I have this P and A. So it's very similar for people who are familiar with physics-informed neural networks than pins. Like these are your collocation points. So how we do that? Well, just sample the torch values of those parameters. We create 3 data sets for training, develop, and test set. And these are dictionaries with keys for variable names. We create this dictionary data set that will be readily used with PyTorch data loader. So for anyone familiar with PyTorch, like this is standard thing. We are not changing anything in terms of data loaders at all. So in terms of sampling the parametric space, here I'm visualizing this 2-dimensional parametric domain where I have parameter P and A, and the blue is a training data and the red one is a test data. So each dot represents the point in this parametric space on which I'm going to evaluate the objectives and constraints and train neural network to satisfy those. So first I need to have neural network to represent this primal map architecture. That's the mapping that will take in the problem parameters and generate primal solutions. And I want to have it symbolic. That's why I wrap it in this node class. Next, I'm going to define these objectives and constraints. So for that, my neural network will generate X. Yeah, and this will be symbolic variable, but I know that it will be 2-dimensional tensor because first dimension will be number of samples in the batch, and the second dimension will be the dimension of the variable. And this is a 2-dimensional problem. So I can do this slicing to generate X and Y variables, and I will generate these P and A as problem parameters. And now I have the symbolics that is needed for me to construct this constraint optimization problem in like very intuitive way. So this will be my objective, which I want to minimize, and these are the constraints I want to satisfy. I can add some names just for nicer plotting. Once I have all the constraints and objectives, I aggregate them in a list of objectives and list of constraints, like we would be used in like CDXPy or PyOmo. But what is different with those, then instead of numerical solver, now I'm specifying the trainable architecture, the neural network that will come into these components that will be trained using some sort of differentiable loss function. There are different ways how to do that. The simplest one is penalty loss, and that's what I'm going to show you here, but you can also go through penalty barrier functions or augmented Lagrangian type methods that basically get you scalar valued objective term based on objectives and constraints. So I'm not going to go into like details of the optimization theory here. If you are interested in more details, like you can look at the implementation of these loss functions in the library. And now I have everything I need. I have differentiable constraint optimization problem where I will learn this neural network to satisfy these constraints and minimize this objective. And I'm going to use stochastic gradient descent for that. So I'm constructing the trainer and going to run this training. I guess it will take a while, but after training, I will see when I plot the solution, let me quickly just skip over here, is that this neural network will be somewhat close to the solution obtained by numerical solver, like interior point. And you can change the parameters every time of the problem formulation and see how the solution changes. So that was the GIF I was showing. So, okay, so this is example for learning to optimize. And in the interest of time, I want to show you more examples. So there is a question, maybe I missed it, but can you briefly explain what exactly happens when you formulate an optimal control problem in Neuromancer? Is it doing imitation learning of the real optimal control problem using it as a data source or utilizing PyTorch for numerically solving it? The latter one, but we are using stochastic gradient descent on the distribution of the control parameters on the closed loop system problem rather than using like interior type point methods. So let me show you another example. I will get to the optimal control problem really soon. I want to show you this physics-informed neural network because it's conceptually almost exactly the same, and in a syntax way, exactly the same what I just showed you for learning to optimize constraint optimization problem. Here, we want to train neural network that satisfies some PDE constraints on collocation points and initial and boundary condition. So, very influential paper by Raisi, Perdikaris, and Kariniadakis. Again, we start with some problem formulation. This is the PDE equation. I have some initial and boundary conditions, and I'm going to sample those. So let me skip how it's being sampled. Just let me show you the visualization. You see, again, we have two-dimensional domain for this academic example where X is a spatial domain, T is a temporal domain, and we have these blue collocation points. These are the points on which we want to enforce the PDE constraint. And we have these red initial and boundary conditions on which we will have supervised learning signal. So all you need to do, again, is to sample these and create the sample data set and hand it to the PyTorch data loader. Specify your mini batching and then you want to shuffle the data or not. So like all standard thing in PyTorch. And now we are going to define the neural network that is going to solve this PDE exactly in the same way what we did in the constraint optimization problem. So I have some multi-layer perceptron that will be mapping spatial and temporal domain into the solution of this PDE. All right, then I want to enforce the PDE constraint. So that means that I need to have information about the first and second gradients of this neural network with respect to time and spatial domain. This is as easy as, again, exploiting the variable construct in Neuromancer, where this y hat will be solution of the PDE, t and x, these will be spatial and temporal domain. And now all I need to do is to call gradient, the grad of t with respect to y hat to get the symbolic gradients. And now, because I have the symbolic derivatives, I can construct this PDE layer in one line of code with this symbolic expression. And this is PyTorch NN module. And again, you can evaluate it with tensor dictionary on input. And you can visualize the computational graph of it. It's quite messy because a lot of terms. But what it allows you to do, again, is to impose objective terms and constraints on this symbolic expression. So I know that this pin needs to be equal to 0 because it will represent the residuals of my PDE equations on a collocation point. So that's what I'm going to enforce over here. That's this objective term here. Minimize the residual PDE on collocation. Then I have initial and boundary conditions that is supervised learning loss. So the output of my neural network needs to match the exact solution I have provided from the data. So that's to supervise learning on initial and boundary conditions. And you can add additional constraints depending on your application. So here are some inequalities to keep the solution of the neural network in interval -1 and 1. And altogether, you will have 3 terms in your pin loss function that you put together as these objectives and constraints and create the differentiable constraint optimization problem. Again, exactly the same syntax like for learning to optimize, and instantiate stochastic gradient descent and train this neural network to solve the PDE, to satisfy the objective terms and PDE constraints over the distribution of the collocation points and initial conditions. So after training, you should see that solution of the PDE is matching the ground truth PDE and can avoid the residuals. So the same idea. The question, how does the Neuromancer scale to larger problems, say from Burger's equation to incompressible Navier storks in 2D? Yeah, great question. So Neuromancer is not developed for like high performance per se. It is built on top of PyTorch. So I would say you may have more efficient implementations in JAX or Julia, because that's the nature of the underlying backend. So that's the first limitation, that PyTorch is somewhat a little bit slower. So we traded the performance for user friendliness and minimalistic user syntax. Yeah, but with current accelerators, like you can use a bunch of GPUs and still like exploit PyTorch on high performance computing if you have the computational capabilities for that. Yeah. Okay, so I have shown you learning to optimize, constraint optimization problem, and learning PDE solutions with pins using exactly the same syntax. Now, my next step would be showing you system identification of differential equations. So let's say you want to do neural ODE. And you have some dynamic system that generates the data, and you want to fit black box model to this data. And the black box model will be neural differential equation. So as opposed to having like the samples of the parametric space before, now we have samples of trajectories, samples of rollouts. So that's slightly different in this dynamic system setting when you're learning the operator instead of direct solution. But again, we can use exactly the same building blocks. Here is multi-layer perceptron that will define the right-hand side of my differential equation. And I want to make this continuous time model. For that, I need to solve this with some ODE solver like Runge-Kutta. And there are 2 different ways. You can either like use back propagation to time, compute the sensitivities of this model, or use adjoint methods. So adjoint method is basically what is behind this neural ODE equation. So very influential paper, everyone knows, I believe. So what we provide in the library is implementation of a list of ODE solvers. You can check it yourself, like Runge-Kutta, or like this more fancier one like multi-step methods that allow you to do this back propagation through time. Or we also provide interface for this differentiable equation integrator that implements adjoint method. So now you have this neural network. You provide the ODE solver with some time step or select the numerical method, and now you have this discretized ODE solve that can be used in a symbolic setting again. So we wrap it in the node, and I expect some states on input and states on output. And I provide this model to the system because I want to do rollout over n steps. So this would be my unrolled symbolic neural ODE into like 3-4 lines of code. And now I want to define some system identification loss function on top of that. Like here, I want to minimize the residuals between the prediction and the sample trajectories from the ground truth system, and I may want to add some extra terms like boundary conditions, or want to add this finite difference loss to approximate the first derivatives. So I can create like new variables for that just by implementing this difference. That will be my two objective terms that will basically represent this optimization problem now. I want to train the parameters of this neural network that will generate the trajectories of the ODE discretized over time with predefined prediction horizon and minimize these two objective terms. So it will be as simple as that. Again, exactly the same syntax as I use for pins or constraint optimization problems. And using exactly the same trainer and stochastic gradient descent, and after training, you should see like rollout of your trajectory compared to the ground truth. So that's system identification capabilities in a black box way. If you want to do it in a white box way, we also provide you with that option. For instance, let's say I know this differential equation, but the only thing I don't know are the parameters of this differential equation, this alpha and beta. So for that, I don't need to use black box neural network to represent this right-hand side. I can just write the differential equations over here. So this ODE system is our base class for ODEs that is still NN module. So all you need to do is to just implement your right-hand side of your differential equation and define which parameters are trainable, which we want to identify from data. So you can do parameter estimation of ODEs. And again, exactly the same syntax. You can also do what is called universal differential equations, very neat concept, just basically gray box modeling when you combine black box function approximators with white box components. So all kinds of system identification models that now can be used for control. So hope I still have some time to show this example where I'm going to solve this reference tracking problem for this canonical control problem of two-tank system. So this is defined by two nonlinear differential equations where x1 and x2 represent the levels of the tank in 1 and 2, and my control variables are the pump modulation over here and the valve opening. So this is two-way valve. So it has a bilinear relationship over here. So nice small scale nonlinear optimal control problem. So now how can I solve this optimal control problem? So objective here is to not to solve with one specific scenario. We want to solve it over the distribution of control parameters. So we want to learn policy that optimizes over distribution of initial conditions, different desired reference trajectories, and different constraints. And we will do this again by sampling these, propagating forward to the control policy that will be neural network to generate control actions. And the system model can be state space model or neural ODE or Y-box ODE as I showed before. So I will use exactly the same API that I use for system ID for doing this control. Formally, the optimal control problem is defined as this parametric optimal control problem, where I want to minimize over the parameters of the control policy that is differentiable function, like neural network, or can be polynomial, can be anything that you can compute gradients of. And it's mapping your states and desired references or other control parameters in control actions that perturbs this dynamic system model, can be differential equation, and you have some optimal control objective terms. So regarding to previous question on value functions, well, this objective will give you the exact value function, right? Because everything is model based. You have the model of the system and you have all the terms that go to your quote unquote reward. Yeah. And you can optimize this by running stochastic gradient descent through this computation graph over the sampled initial conditions and desired references. So it's different than solving model predictive control type problems, where for each instance of initial condition and references, you would need to call iterative solver like interior on point or active set method to obtain decisions on your control actions. So that's classical optimal control approach. Imitation learning approach would take the solutions from the model predictive control and learn neural network to mimic the solution from MPC. But that requires the solving the MPC in the first place. Here, we don't require that. Here, we just exploit the knowledge of the system model and objective terms and the differentiability of this computation graph. So we can compute the sensitivities of the problem to train the control policy parameters. So you can really think of it as a model-based policy gradient approach. So I will skip this training dataset generation, very similar. Here I define the ODE, select specific integrator, make it symbolic, get the candidate neural network approximator for the control policy. Here I pick this multi-layer perceptron with hard constraints on input outputs. That's easy to do with projections. And I wrap it in the symbolic node again and make it a closed loop system over predefined prediction horizon steps, which I can train on a given objectives. Here is like the reference tracking. These are state constraints. These are some terminal constraint penalties, and you put it all together in a list of objectives and constraints and hand it over to the differentiable problem. Again, exactly the same API that I used for previous applications. And I use stochastic gradient descent to train this model, and I should obtain control policy that generalizes over the distribution of initial conditions and distribution of the reference trajectory. So it's truly parametric solution. Yeah. So as you can see, it's again approximate solution. There may be some small steady state offset. For that, you will need to deal with some fancier methods that integrate like the error. So having some feedback loops, all kinds of things can be done. And that's why it's exciting, because all what we develop in classical control theories and differential equations can be now translated into this new differentiable programming paradigm in end-to-end trainable way. Okay, I think we are almost at the top of the hour. So in summary, Neuromancer is open source SciML library written in PyTorch that integrates deep learning, constraint optimization, pins, and like control theoretic concepts for all sorts of scientific machine learning applications, from solving PDEs, solving optimization problems with constraints, learning surrogates for dynamical systems and control. So if you are interested, have a look at our GitHub, try examples yourself, create issues, find bugs, show us new examples in your applications, and we will be more than happy to receive your feedback. And here are just acknowledgements for our amazing team and contributors from PNL. And I would like to thank you very much for your attention.
Thank you, Jan. That was a very thorough tutorial on what Neuromancer can do. I think it's a couple of questions on the chat. I don't know if you replied to the last one. By Eken says, is there any support for implicit integrators?
As of now, we provide interface for the adjoin method, and we have a list of explicit integrators implementing the library. So we don't have direct support for implicit integrators, but with sufficient manpower and time, it can be implemented. Like these are just numerical solvers that it's not, there is no technological barrier.
Okay.
Yeah.
People can also contribute to the
repository. Oh yes, we are more than happy to make this community development. So we started this as a project at PNL, but we went open source, and the intention is to really like make it useful for community, for early career scientists who are doing rapid prototyping, testing new ideas. So that's what the library aims to provide. It's easy to set up and get some quick results. And once you have your architecture and everything is set, you want to scale it to very, very large systems, exploiting high performance computing. Maybe you want to like go implement it in C++ or in JAX or some other high performing language that can be.
Okay, cool. If anyone has any more questions for Jan, please type them in the chat, or you can raise your hand.
Yeah, I have one question here.
Yeah, go ahead.
Yeah. Well, first of all, thanks for this great presentation. It's awesome. I've been following you on LinkedIn, and I'm very impressed by this work. As you said, it bridges like the control theory with a lot of like machine learning and adaptation and so on. In the second example that you were discussing, you basically said there could be multiple formulations of the problem, such as like when you are casting the optimization problem, it can be formulated. The Lagrangian can be formulated as any form, but the actual solution for computing the gradients and all that is in a stochastic gradient. Is this what I learned from it?
That's correct. Yes. So what you are doing with this constraint optimization setting is you are shaping your loss function like you would do in pins. And whether you do it with penalty methods or augmented Lagrangian, you're still ending up with some scalar value that you will compute the sensitivities backward through the computation graph and use those sensitivities in a stochastic gradient descent.
Okay. And the fact that you use like an augmented Lagrangian, for example, is this by choice, or was this something that was giving better results than other formulations?
So this was based on some research from the community, particularly from Fernando Fiorento and Pascal van Henterning, who showed this in the context of power systems optimization, learning to optimize with augmented Lagrangian. Yeah, so we implemented that method in the library. It provides you advantage that it tracks the dual variables as well as compared to only primals in penalty method. But in our experience, it's a little bit tedious to tune because there are a lot of parameters. So this hyperparameter optimization is a thing when it comes to these machine learning models, when they have multiple terms and you need to like balance them properly. And there is more art than science at this point, or like brute force computing.
Sure. Thanks.
Yeah, but it can provide you with a lot of advantages to having the dual variable information.
Right. And differentiability is assumed here, right?
Yes. So the primary assumption that every single component you are having is at least one differentiable almost everywhere. Yeah.
Thank you.
Thank you very much.
Thank you, Ahmed. I think it's 5 p.m. at the moment, so I think we're just going to leave it up to here. So that's okay. So thank you so much, Jan, for sharing your work with us. And accepting to give this talk. It was very informative.
Thank you very much, everyone, for joining. It was a true pleasure.
Yep.
Have a great evening, everyone.
Have a great
day. Bye-bye.
Bye-bye.
Żono, możesz?